Hi everyone, I'm Micaiah and this is my report for Lab 2, Lines of Charge. The purpose of this lab is to create a more accurate model for calculating the charge on the pieces of Scotch tape by using a new computational model with the same data from Lab 1. Some physics principles to keep in mind are conservation of charge. Charge cannot be created nor destroyed. Coulomb's law, the electric force. Newton's second law, F net equals ma. Newton's third law, reciprocity of forces, and the superposition principle. My results for the charge calculated by my new code is 3.69567 e to the negative 8 coulombs. So here's a quick recap about the experiment. I observed different interactions involving the U-tapes. Two U-tapes repel each other. A U-tape is attracted to a negatively charged pin, which means that the U-tape is positively charged. Here are my measurements from Lab 1, which I used to help me in my calculations of the charge of the tape modeled as a point charge. Since F net is 0, I set Fe equal to Fg and solved for Q and plugged in my data. For the new computational model, some assumptions that I made were to ignore air resistance and the charge is evenly distributed among the length of the tape. The lines of charge versus point charge model. It uses the same data for both codes. However, with Lab 2, we're dealing with multiple point charges instead of one. We can think of the pieces of tape as electrically charged rods. The procedure to calculate the E field is to divide the rod into smaller point charges, calculate the E field of each piece, and add all the pieces together, which is superposition. The changes that I made to my code were adding my own data, such as tape mass, position of the tapes, etc. An interesting problem with Q. The point charge Q does not work in this code. The electric force and gravitational force weren't equal in magnitude. This makes sense since each piece of the tape only has a fraction of the total charge. With trial and error, I was able to find Q. I also added my electric field function from Lab 0 that calculates the electric field of a point charge. Here in the nested for loops, I take each section from the top tape and calculate the electric field on the section due to the bottom tape directly below it. And then I calculate the electric force between those pieces by multiplying the top section's charge by the electric field that we just found. The loop will continue to run until it does this for every piece within the top tape. Here we can see what my code looks like when we run it. The red balls are the top tape, the blue balls are the bottom tape. The right arrow is the electric force, the yellow arrow is the gravitational force, which are equal and opposite in direction. The green arrows are the electric fields of each section of the tape. I added the link to my code so everyone can take a further look at how I was able to create my computational model. What if you had modeled each of your tapes as a single point charge, like in the previous lab? They would have been the same value of the point charge as calculated before in Lab 1. Why do these estimates differ? Which value is more likely to be closer to the real value and why? We are considering a single point versus multiple points. That required the superposition principle to calculate the net electric force. The line charge value is more accurate since it takes into consideration the different directions when calculating the electric force. To conclude, the labs helped demonstrate the transfer of charge between everyday objects, visualize Coulomb's law, as well as Newton's third law, and I learned that the line charge model is more accurate than the point charge model. Thank you so much for watching, and I'll come back with more physics fun.